how can we do better? So in terms of either organizing the challenge or how do we run this open source community in a better way? We are very open, and I'm actually happy if there are other universities who want to lead these efforts. Or if you want to host the next MagNet challenge, I've started to think about it. What do we do? What's the next challenge? But I'm happy to hear your opinion, and happy to, if your team, your university is ready to host the next challenge, I'm happy to pass it to you guys. So that's all I have, and I guess I will open it up for question and discussion time, and then we can move on to team presentations. Anyone has any comments? Okay, maybe people are shy, so we will go ahead and start the team presentation. Let me see which teams are on the spot. So today is pretty light. I guess everyone is waiting to see how other people run this, but that's fine. So we have, I think we have 3 teams sign up for today: SAL, Triphoven, and Bristol. So how about we start from SAL? Jacob?
Yeah, we can start. We planned it in such a way that Martin will start with his part. I will go over the learning part, and then we go over to Martin again to the evaluation part.
Sounds good. Yeah. So yeah, as I said, today is pretty lightweight. We have a lot of time, so feel free to go dive into details, and we're happy to learn what you guys learned.
So hello from my side. I'm Martin. I hope you can hear me.
Yes.
Yes.
I want to first talk about how the data for our model was generated. So I mean, I first went through all the materials which were given for the all 10 materials where we have all data given. And I think how I read this data is irrelevant. So I want to describe how I get the data, and this was done. I called it get NN data function. And so basically what I did was making the FFT from the data. So first I checked all the dimensions and stuff and created the respective variables. And then I did the FFT for every waveform we got. So this means we got the same number of elements for the FFT values and for the frequency of these values from the FFT. And the basic idea was that the FFT basically says how much energy at which frequency is injected into the magnet. So the loss should be some function of this. And after I did the FFT for every part or for every waveform, it is important to scale this for further use in a neural network. So I divided each waveform, P waveform, the FFT we got from there, to the maximum, and stored the maximum in the respective table then. So we then have for every material the data, the FFT data in frequency and waveform, in the FFT frequency and the FFT data, and the respective scalar. And then we have the temperature, material ID, and the loss for evaluating our model then. And so this is basically the idea. And then we need to scale the whole data to 0 and 1, between 0 and 1, because we only scaled the frequency and respective FFT data, and all other data such as the temperature, the material ID, the scalar of these FFT data are not scaled. So I've done this via a pandas dataset, and I have here basically scale all the elements which I said prior, which are not between 0 and 1. Yeah, and I think that's it from my side now. And then I exported the data frame to a pickle file and gave it to Jacob for training.
So this is pre-processing of the data.
This is pre-processing of the data. So I pre-processed the data for the neural network. And so I have done the FFT and scaled it appropriately so that the neural network then can learn on this data.
Great. So basically you do a FFT and then do the scaling. That's what this code is doing.
That's what this code is doing, but it's important that the scaling is divided into two parts. So I scale the frequency and the FFT values for each waveform. And then I scale the scaler. So basically the idea is that the frequency changes for a specific waveform and in another way that the frequency changes for another waveform. So I scaled the frequencies of the respective waveform down to 0 and 1 and not overall.
How do you so once you do the FFT, do you take the first few harmonics of FFT, or how do you divide the threshold? I guess the purpose of FFT is to compress the time domains information in some way.
Yeah, basically I only did the FFT, so I have done nothing with harmonics and so, because this should so the neural network should work with these harmonics.
Okay.
Yeah, so I basically only did the FFT. And what I forgot to mention, I think, is that I have reduced the number of the waveform.
Mm-hmm.
So we have, I think, 1024 points given, and which is quite a lot. So the respective or the important data from this waveform needs to be stored in less points. And even if you have a data sheet, you don't get the 1024 points.
Right.
And it also then helps to decrease our model size. So I basically only did some linear interpolation and scaled it down to 265 many interpolation points.
Mm-hmm. Great. Oh, by the way, I want to introduce our team members here. I see Haran and Shukai and Tom, and also Professor Dragan Moskvovich here. Maybe the teams can introduce yourself a little bit and ask questions as well. Haran, Shukai.
Yeah. Hi, everyone. I'm Haran Li. I'm a graduate student in Professor Chen's group, and previously I'm also working on this magnetic colors measurement and also the modeling with neural network. And here I'm one of the executive committee to go through all the code and evaluating the results. And yeah, we're happy to see everyone here.
Yeah, great.
Hi, everyone. My name is Shukai, and I'm a third-year PhD, and I've been working with Haran for a couple years on this project now, and also part of the executive committee. Very excited to see everyone with their results. So I have some questions. We'll go ahead and ask. And
yeah.
So, yeah.
Yeah, Haran basically evaluate the model accuracy, and Shukai evaluate the model size. So some of you may have reached out to them regarding if we find any uncertainty or something that we were not 100% sure about. And Tom? Thomas, are you there? I saw the name. Anyway, he may step out a little bit. Dragan, Professor Masmovich, I saw your name.
Hey, hello everyone. So this is Dragan Maksimovic, University of Colorado Boulder in power electronics. I'd like to actually take this opportunity to thank Minji and the team at Princeton for the fantastic work in initiating this challenge and then conducting the challenge. It's been really great to see how many teams participated and achieved great results. This was an extremely well organized challenge that I think teams and the overall power electronics community will benefit from. So thanks all for your great work on the challenge.
Yeah, it's all really a teamwork, like not just us, it's the entire all the universities coming from the world. We're pushing this problem.
I know, but really putting this opportunity for everyone to participate is really crucial. So I'd like to thank you for that.
Thank you, Dragon. And I also want to mention that the judge committee, some of them we invite all of them, and they may show up in the middle of the meeting because they are all very busy. But we will consolidate all the information. And the how it works is that the executive committee, me, Haran, Shukai, and Tom, we will read all the reports and we'll create a summary for all the teams. And we'll present the accuracy and model size and the general approach that you're taking. And one of the purpose of these town hall meetings, really, we try to capture what we are missing. So it could be that you have really neat idea, but we didn't get it through reading a report. So this is an opportunity for us to really make sure we understand the best part of your model. So yeah, but again, it's not tied with how you present it or the quality of the presentation is not a part of the evaluation process. Yeah, again, thanks everyone. Jacob, go ahead. Sorry for I feel it's good to introduce our side as well.
All good. So yeah, then we went over to learning. Here now I will start with what didn't work. So first, our first concept was that we wanted to use graph neural networks. And we tried this until we had to submit the first report in November or October, I don't remember, end of October, beginning of November. Right. The thing is, this problem is really hard to put into a graph neural network because it is just not a graph. we tried to massage it into a graph really hard, but it just didn't work at all. Yeah, and from this graph neural network, we wanted to then using symbolic regression, we wanted to extrapolate basically a model from those neural networks which sit between every point in the graph. So yeah, this didn't work. So then we had to start over from scratch. So then we went an easier way and said we will go to a fully connected neural network. And that's what we did. So we had 516 input points. So these were the 265 points of the reduced waveform, 256 points of the FFT, the material ID, and the temperature. And we just directly fed them as input. So no peaks or whatever, just pure waveforms. And then we reduced this. We started with the whole 1024 data points, and then we slowly reduced this to the 500 because this worked better. And we didn't have time to go smaller and smaller and smaller because this takes a while until this trains. Yeah, here you see the remnants of all the trials we had. So it was just really a very simple network, linear, connected with ReLUs. That's it. And a linear ReLU stack, very simple. As optimizer, we used AdamW because we knew that we have a lot of parameters, so a lot of them will be not relevant. So, and AdamW just really works well with sparse networks. So we said it's good if we can put a lot of the weights down to 0. We use the standard mean square loss, and I opted for this scheduler because you can nicely tune it when it should go down in learning rate, and it worked quite well. Yeah, this is how we trained. All the other stuff is just data input and output. Any questions?
So for graph neural network is very interesting. We originally started from, I can share our experience. If you trace our publications, the first thing we try is the wavelet transform. We went through the process. So originally we were very ambitious, and Haoran, I think that was 3 years ago. We think, oh, okay, let's do a transient. Let's model the core loss with transient behavior, not even periodic steady state. And then we apply wavelet transformation, get a graph, and then map it. So that they are, I would say, thinking from the graph perspective is a really good concept, because the other possible approach is you can think about BH loop as a 2D graph, and the BH loop will change as the excitation waveform change and temperature change. So that's the other possibility. But again, well, the one of the purposes why we initiate this challenge is that we don't know which one is better, and indeed there has to be a lot of trial and error, and that's why sharing what has worked and what hasn't worked is very, very useful.
Yeah, so I really like graph neural networks, and they are very promising, but just some problems are not meant to be in graph form. So
yeah. Maybe you can go back and try it again. Now you don't have the obligation of winning a challenge now.
Yeah, exactly. Maybe we can.
Yeah, great. Cool.
That was basically, what we tried in the last month.
So then what's your thoughts? Like, what do you think can be better for the challenge, and for what are the remaining problems, or what are the interesting do you have any other thoughts that you want to share with us?
So we were pretty astonished now that our losses were so bad. So our results.
We were actually surprised, because
it's super. Yeah, I'm still a bit surprised by that, because our average losses for the other materials is below 1%.
Right. So did you guys check if there's any error? Like, we were hesitating whether we should reach out to you guys, because you guys performed well in the qualification stage.
We will now check because maybe we did an error somewhere.
Go ahead and check if there's any like units error or somewhere there's a coding, because we think it's unfair to provide information to your team, because it is what it is. But now for publication or for other purposes, I would say, yeah, go ahead and check, and maybe there's just like a small error you want to fix in the code. Yeah. Okay. Go ahead.
What did I want to say? Yeah, I think with more time in training, we could probably reduce the number of neurons even more.
Mm-hmm.
Just get it down and down and down, and you just have to, slowly go down until you find the optimum sweet spot. But again, it trains a day or so every network in this size.
Right.
What else could we do? We could probably also reduce maybe the number of data points we put in, so even go lower than the 256 to do that. So there's still a lot of things we can do.
Mm-hmm. I guess once we open source all the reports, you can go ahead and look at the models that performed well, and that quickly you don't have to try all of the possibilities. The other thing is, I don't know if any of you guys are familiar with the ImageNet competition. They run a competition, but the server actually was up all the time. So that's what we are trying to do also. So after the challenge, once we have some time, we'll launch a server, and also everyone can upload your model and then immediately beat other people's model. We'll maintain a dynamically actively updated like competition, but there's no award associated with that. But it's just like your team can rank #1 if you have the best model. Okay. That's great. Thank you, and we will move on to the next team. And feel free to comment and jump in when other teams are presenting.
Sure.
It's not really we hope, that's why we call it town hall meeting. Feel free to jump in and present and ask questions and share your experience, by the way.